optics. They have innovative solutions for optics and photonics, and he's already coming on stage. Thomas Schuffenhauer, he is project manager for laser optics. And with no further say, stage is yours.
Yes. Thank you very much for the kind introduction. So, my name is Thomas Schuffenhauer. I'm from SIL Optics, a small company in Franconia near Nuremberg. And I will talk a little bit about optical systems for qubits with trapped ions.
I'm not happy.
As soon as we have the slides.
I'm not happy about how they have the organization with the presentations.
That's from before the slides. Yes. Perfect. No worries. So let's start. We are SIL Optics. We are a pretty old company, 130 years almost now since the founding or foundation. And we are located, as I said, in Franconia, and we have around 250 employees. Let's see. First of all, just very briefly, I will go across these slides very quickly. Our portfolio can be divided into laser optics and imaging optics. I myself work as a project manager in the laser optics. And the products here range from f-theta lenses, for example, for additive manufacturing, beam expanders, aspheric lenses, and also special lenses or lens systems such as trapped ion lenses, which I will focus on in this talk today. And yeah, as you can see, more of half our laser optics products are custom or custom-made lenses. In the imaging optics, we have custom lenses, portfolio lenses, and special lenses. Special lenses means these are big imaging optics, for example, for the IR range. And they are available only on request, so we don't have these in our portfolio per se. Also here you can see big part of our products are custom lenses. What are the applications and markets for our products in general? So very widely ranged here. You can see laser material processing, such as laser cutting, laser drilling, stuff like that, laser structuring. But also in the semiconductor industry, the process monitoring field, and which is already highlighted here in quantum optics, which is a rather small part of our business, but we've been developing and manufacturing trapped ion lenses for the last 15 to 20 years. And I will now talk about these after this slide here, which is another part where we are also involved in several research projects, so fundamental research. This here is one example of a research project which is also which involves quantum technology in general. So here it's a medical application, cancer diagnostics basically, and we want to develop a new imaging technique by using entangled photons, which should be able to make the imaging in the clinical setting much more efficient. But enough of that. Let's continue with the quantum computing and the main technologies here. So as you can see, there are many different, and as you can already also see in this whole exhibition here, there are many different approaches to generate qubits, which is the basic processing unit in quantum computing. Of course, you know, classical computers used binary bits, zeros and ones. And in quantum computing, you can have a superposition of 0 and 1. And here you can see in the case of trapped ions and cold atoms, you use laser light to manipulate these qubits, and you use the lasers to manipulate quantum energy levels in this case. So how can this be realized? You have a Paul trap, which is basically the ion trap, which is placed inside a vacuum, and you have in this setup you have 2 electrodes on the poles and the ring electrode, and by altering the electrical field with a very high frequency, you basically trap the ion inside such a trap. It's cooled down approximate or almost to absolute zero to do that. And you can imagine this, so this is a mechanical model which is shown here, by putting a ball onto a saddle shaped, or onto a saddle shape, which represents the electrical field. If you just have it, if you don't alter the field, the ball will just roll off this field. And if you turn the saddle, or if you apply an AC voltage, you can stabilize this ion in the electrical field. And as I said, you do this by applying a very high frequency to this electrical field. So now we have a trapped ion. How can we manipulate this trapped ion? One process is the so-called laser Doppler cooling. As you know, in physics, very simple. Cold medium means low speed. High temperature medium means high speed of the particles or the atoms. And laser Doppler cooling now works that you cool down the trapped ions by shooting a photon onto the atom, and by this you excite this atom into a higher energy level. This excited state then remains for a certain amount of time, and as soon as the atom falls back into its ground state, the photon is spontaneously emitted, and this emission is done with a random direction, and this basically decelerates the atom, which means it cools down the atom further. So this is one way of cooling or of manipulating trapped ions, which means you basically can cool the ion down. And so where do our optics come into play in this whole universe? So here is depicted a typical setup for research, basic research of trapped ions. So you have a vacuum chamber. You have a vacuum chamber with the ion trap inside. You have a vacuum window, which allows access to the trapped ion. And this whole thing is cooled down to, as I said, almost absolute zero. And you then, I don't know, does this have a laser pointer here? No. Okay. So you then have our lens, the trapped ion lens, next to the vacuum window. The lens needs to have a very high numerical aperture to allow focusing, very sharp focusing, to allow the manipulation of the trapped ion. And you then have several other optical components, such as a beam splitter, and you have a laser and a beam expander. So let's see how this works. You shoot the laser, you magnify the laser first, then you shoot the laser onto the beam splitter or a mirror, very simple, and you go through our trapped ion objective, and you focus onto the trapped ion with a very specifically modulated laser light, so it must be very perfectly tailored, depending on what process you want to trigger. And you then collect the emitted light, or you collect the information of the trapped ion back through the trapped ion lens, and you image it onto your onto your CCD chip or whatever imaging tool you're using. So this is what our trapped ion systems are used for. And so if you want to have such an optical system designed for your setup, if you're doing fundamental research in this field, we're always happy to design something. For that, we need several specifications to get the best solution for you. We need the vacuum window material, so if it's fused silica, if it's an optical glass, we need the thickness and diameter, of course. And yeah, you can see all the other things. We need the wavelength, which I forgot to mention. The wavelength is very important because many of these systems require color correction to allow focusing of different wavelengths and imaging of different wavelengths. So this requires optical glasses to chromatically correct the whole performance. Yeah, so always happy to design something like that and to provide solutions. We also have a small booth in the front of the hall. If you have any questions or concrete inquiries, don't hesitate to ask us. So yeah, that's it for me. Thank you all for your attention. Yeah, looking forward to your questions.
Thank you very much. And let's see if we have some questions in the room. You said, where is your booth?
Right in front of the hall.
Okay.
2A25 is the.
Okay, perfect. So if you wanted to catch up as a one-on-one, then they'll meet you there. Yes, I think there are no more questions. Thank you so much.
Thank you very much.
Great to have you.